Assalamualaikum. My name is Ahmad Syazami Syamsuddin. With my teammates Ahmad Hakim bin Ahmad Ilmi, Muhammad Aniki Putra bin Awang Abdul Hisham, Muhammad Afham Al-Hafiz bin Muhammad Rozalil, and Ahmad Muaz bin Nur Helmi. We are from Department Mechanical and Aerospace Engineering, IUM. For this project, we are under supervision of Dr. Dwi Pembianti from Department Mechanical and Aerospace Engineering, IUM. So today my team are going to present our proposed project for driverless vehicle category, which is about real-time ADAS, deep learning and sensor fusion. So the vehicle concept we choose for our vehicle is an ADAS, which is Advanced Driver Assistance System, which is designed for a robust performance in urban development such as metropolitan city, that focusing on real-time object detection and lane recognition to improvise the safety of vehicle and driver during driving. The design approach we choose is we will use a multi-sensor fusion strategy that combine high-resolution visual data from cameras with precise 3D mapping and object measurement from radar sensor. The development strategy we use we will integrate deep learning model such as CNN and YOLO with common filters that will ensure the system reliability despite the variable of lighting and traffic condition.
So for my part, I will explain about the convolutional neural network CNN. CNN are utilized to identify complex spatial hierarchies and visual patterns, which allow the system to accurately track road boundaries and lane markings. So for the next one is YOLO, you only look once. It is a high-speed framework employed for simultaneous bounding box prediction and class probability estimation. By combining these two technologies, the system achieves a rapid detection of pedestrians, vehicle, and other critical obstacles. This dual algorithm approach ensures that the vehicle can distinguish between its environment via CNN and the dynamic objects within it via YOLO.
For my part, moving on to the core of our perception system, sensor fusion. Sensor fusion involves merging data from various sensors to provide a more comprehensive and accurate view of the environment. In complex urban environments, relying on a single sensor is a safety risk. To understand why we use fusion, we have to look at the individual strengths and weaknesses of our hardware. On one hand, we have the camera. It is excellent for 2D pattern recognition, identifying traffic signs, lane indicators, and vehicle types. However, cameras lack that perception and struggle significantly in low light or poor weather. On the other hand, we have panoramic 3D LiDAR. These sensors scan 360-degree continuously at high frequency. It allows the vehicle to detect objects in 3D space with incredible resolution and accuracy, regardless of lighting condition. But LiDAR alone cannot read a street sign or see the color of a traffic light.
When paired together, these sensors can transcend their individual limits and give accurate and reliable data for object recognition and tracking. In autonomous vehicles equipped with multi-sensor systems, synchronizing sensors that operate at different acquisition rates is crucial for effective sensor fusions. Cameras, which are solid-state sensors, can capture data at high frequencies, providing a steady stream of image. Furthermore, this high frame rate is essential for tasks like object recognition, lane detection, and real-time decision making. On the other hand, LiDAR sensors, which rely on internal rotating mechanism to scan the environment, typically operate at much lower frequencies, often around 10 to 20 Hz. In conclusion, the integration of camera and LiDAR sensors in ADAS offers significant potential for improving vehicle perception and safety.
Next, I will explain our system's prior experience and capabilities. First, real-time processing. Our system is able to detect hazards within milliseconds during real-world video testing, especially in urban traffic conditions. This means the system can quickly identify objects like vehicle or pedestrian and almost instantly, which is very important for the driver safety. Second, environmental handling. To ensure the system works well in different conditions, we apply training techniques such as data augmentation. This includes flipping images, rotating them, and adjusting brightness. This technique helps the system learn from a wider variety of situations, so it can still perform accurately in different weather conditions, lightning environments, and complex road scenarios. In short, our system is not only fast but also adaptable to the real-world challenge, making it more reliable for practical ADAS application. That's all from this part. Thank you.
All of us are ready for next generation vehicle challenge.